We will be discussing about the linear predictive synthesizer. And also we will be discussing about certain byproducts of LPC. Okay. Like the LPC can be used to improve the pitch detection performance. The pitch detection approach we have already discussed, like that is the time when we learnt about the autocorrelation approaches, etc. Okay. But then we also said that the pitch detection is always not very robust because of the presence of the formants, okay, and the formants tend to introduce some extra harmonics, and that often makes the pitch detection process difficult, okay, when we are using the normal autocorrelation method, okay. But we can still try to continue to use the autocorrelation method, but if we are using the LPC parameter, okay, to flatten the spectrum and all that, so those also we will be studying. So it is not only the linear predictive synthesizer, but also those aspects. And another point that we need to discuss is that towards the end of the last class, there were some doubts which were expressed about the KIs, okay, I mean in the lattice formulation what we had discussed in the last class, okay, we need to discuss, we need to throw some more light on the computation of those KIs, because I mean it was very rightly asked that if we have to do the computation of the autocorrelation in order to find the KIs, in that case what is it that we are gaining computationally, okay. So, or is there any alternative way of calculating the KIs using the lattice structure itself, okay. Now if we see the lattice structure, you see that the lattice structure basically obtains the forward prediction error and the backward prediction error, and this we are obtaining recursively. So it is that recursive structure that proceeds in our lattice filtered structure. So it is not directly obtaining the alpha case, although the main objective of any LPC analysis is to obtain the alpha case. There we are getting the error terms, that's to say the forward prediction error and the backward prediction error, that's what we are getting. But what one can ask is that what is the direct relationship between the prediction errors and the alpha case, okay. There is obviously a relationship, and in fact we just repeat what we said in the last class, that basically the lattice formulation is nothing but the realization of Darwin's algorithm, okay. We have been using the Darwin's autocorrelation method, okay, in order to formulate the lattice structure. So whatever equations we discussed in connection with Darwin's algorithm, that holds good. So the KIs that we are talking of is still the Darwin's algorithm's KI, but there is a different methodology to compute the KIs, and in fact it can be shown that the KIs, instead of writing in the in terms of the autocorrelation, like writing the KIs in terms of the R's, that is what we did in the case of Darwin's algorithm. Instead, there could be an alternative formulation to obtain the KIs from the errors, okay, from the forward prediction error and the backward prediction error. And in terms of the prediction errors, okay, one can write the KIs like this, that KI can be expressed as in the numerator we have m equal to 0 to n minus 1, the backward prediction error, that is the forward prediction error, that is ei minus 1, okay, m, right. M is the index of the summation, and I, as you know, is the recursion step, that is what we are having, and this into b of I minus 1 m minus 1, okay. This is the backward prediction error, and in the denominator term there is a normalized, I mean, for the normalization we have a denominator term that goes like this: summation m is equal to 0 to capital N minus 1 e of I minus 1 m whole square into summation m is equal to 0 to n minus 1 into b I minus 1 m minus 1, okay, and this term square, right. Sorry, here there will be a square term in this case. So this is a square term and this is also another square term. So within the curly bracket what we write is summation of two squared quantities and products of that, and this whole thing would be to the power half, okay. So this let us call, in terms of today's equations, let us call that as equation number 1. So just look at the expression for Ki, okay, very carefully. What we have done is basically a cross correlation of the two errors, the forward prediction error and the backward prediction error. They are cross correlation. In fact, the cross correlation will be given by this quantity, okay, what is there in the numerator, and the denominator is doing a normalization, okay, so that what we are effectively getting is a normalized cross correlation between the forward and backward prediction error. So this is nothing but the normalized cross correlation. Okay, and in fact the KIs like this, okay, because it is expressed in terms of this correlation, okay, these are referred to as the partial correlation coefficient. You see that if I have K1 from here, in that case I will be needing E0 and B0. All the E0 and B0 errors will be required. So that means to say the first order prediction errors, or rather to say the 0th order prediction errors would be needed, and then when we use k is equal to 2, then it will be E1, B1, those error terms would be needed, and we will be getting the correlation of those errors. So it is basically a partial correlation, that is what we are computing, that first the E0, first the K1, and then doing the K2 computation, then doing the K3 computation, like that. So again, just remember our lattice structure, okay. In the lattice structure we require first the K1. In fact, let us have a look at this from our earlier notes. So we use the lattice. Yeah. So just this diagram, you see E0 and B0. We already have the E0 and B0, and then we can compute the K1. That's from this expression, because K1 needs what? It requires E0M, it requires B0M minus 1, and we already have that. Okay. So using this E0 and B0 and this delay element, it is possible for us to calculate the K1. And once the K1s are obtained, in that case we will be able to compute the E1n and B1n. Okay. And once the E1n, B1n and these delays they are given, in that case it will be possible for us to compute K2n. So essentially this K1n, this K1, K2, K3, all these Ki's, okay, they also can be computed using this recursive step of the lattice filter, right? And in fact what we have to do is that ultimately, because we have to relate everything with the alphas, okay. Now once the Ki's are determined, okay, obtaining the alphas is a simple step. In fact there we can follow Darwin's approach, okay, because as you know that as per Darwin we will be having the following recursions, that it will be alpha I, ith step, that will be equal to Ki, and alpha j ith step would be equal to alpha j I minus 1th step minus Ki into alpha I minus j of I minus 1th step. Okay. So this we have to do for j up to j varying from 1 to I minus 1, right. So this we already know, and this Ki's, they are called as partial correlation coefficients. Okay, these Ki's, they are called as partial correlation coefficients or as PARCOR. Right. Now there is an this basically gives an alternative. This PARCOR is giving us an alternative way of computing the matrix inversion, right. So that is quite obvious. And now there is a different way of specifying the mean square error, because after all, how did we obtain these coefficients, these Ki's? These Ki's are ultimately obtained by the minimization expression of the prediction errors, right. So by minimizing the prediction errors we had obtained this, but the prediction errors could be defined in a different way, and that is what Berg had done. That Berg had defined the prediction error, the minimization that we are required to perform, that's on the mean squared forward and backward prediction errors, right. So given that, one can write down E, and we write it as E tilde for the ith iteration, and that is equal to summation m is equal to 0 to n minus 1, and then we define it as EIM, okay, this term square, okay, plus BIM, this term square. Okay. So sum of the forward prediction squared and the backward prediction squared, okay, and summed up from m is equal to 0 to n minus 1. So this is our new definition of the prediction error, and we have to minimize this. So if our objective is to minimize this E tilde I, in that case what we are required to do is to differentiate this EI with respect to Ki, and then we have to equate that to 0. So what we have to do is to minimize this. we differentiate this with respect to ki. Okay, now ki we do not see directly into this expression, but please let us remember that what are the expression that we had obtained for the EI and BI in terms of the KIs that we had done in the last class. So, let us see this. Yes, these two very important relations that we had discussed, that EIM could be expressed in terms of EI minus 1M minus KI this quantity, and BIM was expressed like this, the equation 8 and equation 11 of last class. And now what we are going to do is to substitute this EIM and BIM into this expression, call it as equation number 2 of today, okay. And there we substitute this EIM and BIM expression, okay. So there the KI terms are already coming in, and then we are differentiating with respect to KI, okay, and equating that to 0. So if we differentiate with respect to KI and equate to 0, then what results is something like this, that in that case we are getting minus 2, okay, having the derivatives, it leads to this expression. You can verify this yourself, okay, by simply having the differentiation. This is EI minus 1M minus KI BI minus 1 M minus 1. You can definitely expect this because your EI expression itself, okay, is in terms of EI minus 1, BI minus 1 and KI, okay. And this into you will be having BI minus 1 M minus 1, okay. This will be for the EI minus 1 for EIM quantities square and differentiating that, and then for the BIM quantity after differentiation you will be finding minus 2 M is equal to 0 to N minus 1, and writing now the BIM expression, which is nothing but BI minus 1 M minus 1, sorry, M minus 1 minus KI EI minus 1 into M, okay, and this to be multiplied by EI minus 1 M, right, and this will be nothing but the derivative of this EI with respect to KI, and this will be equated to 0, and by having that one can solve for KI. From here you can solve for KI, and KI will be given like this, that KI will be given as 2 times summation M is equal to 0 to N minus 1 EI minus 1 M into BI minus 1 M minus 1. So still it is involving a correlation, but only thing is that the denominator term that differs from the earlier way of writing the denominator term. This time, I mean, from this expression, that means to say that in what we are discussing is Berg's method, okay. So according to Berg's method of defining the error EI, okay, the E tilde I rather, we are going to have KI here as KI. The denominator term will be summation M is equal to 0 to N minus 1 EI minus 1 M square, okay, plus summation M is equal to 0 to M minus 1 BI minus 1 into M minus 1 whole square, right. Sum of these two squares. You see that individually this EI terms summation, EI terms squares summation, and this squared summation, they are to be added. So it is somewhat different from this expression, okay. There we had like the earlier case KI were like this, that the summations products were there, okay, product of the summation. In this case it is sum of the summations, right. So, somewhat different, but anyway using this the KIs can be computed. So, if one applies this kind of a lattice formulation, what one has to do becomes very clear, that one has to feed the S of n, okay, the speech segment, and then one has to obtain the E0 n and B0 n, okay, which is nothing but given here already, that E0 m and B0 m is nothing but S of m, okay, the first estimate, because it is as good as a 0th order predictor, and then obtain K1, okay, out of this in terms of this E0 and B0, and then compute this K1s, and using this K1s you do the filtering, obtain E1n and B1n, and continue until EP of n and BP of n. And then what you are basically getting out of this K1 to Kp, okay, using that you can compute the alphas, and those alphas are going to be your final alphas. That is what you are using for the I mean those are the alphas that you are using in the LPC as the LPC parameters. Now, this is quite an effective technique, no doubt, and let us see that what are the other benefits that one gets out of this LPC parameter. Now, we have seen already that out of the that using the LPC parameters, okay, in this kind of a lattice formulation, what has evolved is that we are getting all this E0, E1, etc. up to EP, B0, B1 up to BPs. So, all these are the prediction error signals, okay, and in fact in general the prediction error signals would be given by this expression, which we have already known, that E of n we are going to write as S of n, that is the signal, minus whatever prediction we are making. So, if in general we make a pth order prediction, then we sum it up from k is equal to 1 to p into what? Alpha k, because k is the running index, S n minus k, okay. So, using the past samples we are predicting this. So, this is all known to us, and this will be written as G of un. So, what we can use is that this form of En, if we now take En to be like our signal, okay, then we will be finding that En is often a very good approximation to the excitation, okay. What is after all this G of un? We will come to this very shortly. In fact, I mean in the speech synthesis model, which we are going to discuss very shortly, you will be finding that we need an excitation, okay, to be given, okay, and that excitation is the excitation which is given to the focal tract model, and as this excitation we can feed this error signal E of n, okay, and the benefit that we are getting from this E of n is that the I mean you can notice that what will be the characteristics of this En. Now, what happens that when the signal suddenly attains a peak, okay, in that case what we are going to do, we are going to predict based on the past samples, but the past samples may be still smaller in magnitude, and then we are predicting the present sample, where the present sample has already attained a larger value, but predicting it from the smaller value will lead to more prediction error. So, whenever the signal changes, okay, suddenly, in that case even the prediction error also will be large. So, a sudden large signal would also result in a large prediction error. Okay. Now that will happen in the voiced speech when, especially at the pitch periods. Okay. Whenever we are having the corresponding to the pitch periods, we are going to have a large peaks available at the S of n. S of n is our original speech signal input, okay, as we are saying. But it is not only in S of n, but even in E of n, we will be having existence of such peaks. Okay. So then can we not use this En signals instead of Sn signals? Can we not use the En signals in order to estimate the pitch? You may ask that what difference does it make? I mean, because S of n is already available to us, so why should we predict and then make a prediction error signal and use that? Well, if you are doing the spectral analysis of this S of n, in that case just remember that S of n is not only going to contain the signal corresponding to the pitch period, okay, but also it will contain some harmonics which results out of the formant frequencies. Okay. The formant resonances would also like to give some extra peaks, okay, in addition to the genuine pitch period peaks, and we already discussed that it is those extra peaks which often tend to give confusing results, okay, whenever you are estimating the pitch period using the autocorrelation on the S of n. So what is the culprit there? The formant frequencies. Now what happens in the case of En is that En is after all an error signal, right? So error signal, what happens is that the error signal becomes uncorrelated, relatively uncorrelated from sample to sample. Okay, so error signal is more having a noise like characteristics. Okay, so it will be uncorrelated. So although the error signal will show some peaks at the, corresponding to the pitch period duration, but at other times other than the pitch period, it will have some kind of a random behavior. Okay, and in the unvoiced part of the speech, it will always, the signal will always have a kind of random nature. Okay. So as a result of that, if we now take an autocorrelation of E of n instead of S of n, in that case what we can expect? Okay. In that case, what happens is that the autocorrelation peaks will be obtained corresponding to the genuine pitch periods, okay, and because of the absence of the formants in E of n, because E of n is having a relatively flattened spectrum, isn't it, as compared to S of n. S of n spectrum will contain the formant frequencies, but by having E of n instead of S of n, okay, all those formant frequencies will be smoothened out, okay, and using the En and a correlation over En, it should be possible for us to get the extra get the autocorrelation peaks, and those autocorrelation peaks will correspond to the pitch periods. So it will be effectively used, this E of n can then be very effectively used for pitch period estimation, okay, as compared to S of n. Okay. So that is one advantage that we are getting by using E of n rather than S of n. Okay. And now we are going over to what we had originally discussed as the title of today's lecture, and that is about the linear predictive synthesizer. Okay. Any questions at this stage on this part what we discussed, because you had some doubts over in the last class, and I hope that that doubt has now been solved. So definitely, when we discussed about the lattice formulation, the doubt was that whether KIs would lead to some extra computational burden, and then that will nullify the advantage of lattice structure. It is not so. So, KIs can be computed in the lattice structure itself, and in fact, what advantage we get in the process of the lattice formulation is that here no such explicit computation of the correlations is required. Okay. One can just keep on recursively compute the error signals, and that itself would lead to the KIs, and KIs would ultimately lead to the predictions. Now, in the linear predictive synthesizer, it would be like this, that we will be having in the form of block diagram, we will be having one train of pulse. So, there will be an impulse generator. There will be an impulse generator, just a train of impulse that correspond to the, what will be the parameter of that impulse? Train of impulse. So, the pitch period should be a parameter. Okay. So, if we feed the pitch period or our estimated pitch period to the impulse generator, then it will accordingly generate a train of impulse at that frequency. Okay. And if next time the pitch period changes, then the train of impulses would also readjust its in between impulse periods. Okay. Now, this train of impulses will be generated for the for what? For the purpose of the voiced speech, and for the unvoiced speech, okay, there will be a white noise generator. So, we will be having a white noise generator, okay, white noise generator, okay, and this white noise generator also will have its output over here, and then there will be a selector switch, and this selector switch we will be referring to as the voiced unvoiced flag. Okay. And remember that from our speech analysis system, okay, linear predictive analysis system, we are also giving the voiced unvoiced flag. First is the pitch period estimation, and then the voiced unvoiced flag that will be provided, and then there will be a gain parameter G, okay, which will basically dictate that what is going to be the amplitude of the speech signal. Okay, so that in the synthesis process also the same amplitude can be used. Okay, and after that we are going to have what? Then in the normal speech synthesizer, what are we supposed to have after this? We are supposed to have the filter, and that filter is nothing but the formant filter, right? So, now who is going to provide that filter? It is using our linear predictive coding, okay, because after all, what is it that we are going to obtain? We are going to obtain S tilde of n, which will be nothing but the synthesized speech, and the synthesized speech can be written as the summation alpha k S tilde n minus k. S tilde n minus k means all the synthesized past samples, and k would go from k is equal to 1 to p, okay, and this plus g u n, okay, u n is going to be the unit step function, okay. So, g u n, so u n would be available over here, okay. So, g into u n, the signal available at this is g is u n, so g multiplied by u n, and that should be added to this, okay. So, this would essentially form our synthesis filter, right. So, this added to the synthesis filter would then generate S tilde of n, right. So, to obtain S tilde of n, what we have to do? We have to make a realization of this filter. Now, realization of this filter, we can have a direct realization, right, using this equation. So, a direct realization of this equation would give us a structure, a filter structure like this, that we will be generating. If we have S tilde n over here, then we have to generate the set of samples S tilde n minus 1, S tilde n minus 2, all the past samples have to be made available to us for the linear prediction, and to make that available, we have to add the delay elements, that means to say z to the power minus 1. So, then S tilde n is here. So, after z to the power minus 1, what we are getting here is S tilde n minus 1 at this point, and S tilde n minus 1 we have to multiply by alpha 1. So, that this would be multiplied by alpha 1, and then it is to be added with this G u of n. G u of n is already there. So, this should be added to G u of n. Okay. So, this is only up to the first sample. So, this is only a first order predictor, but then for a second order predictor, what we need to have yet another delay element, sorry, z to the power minus 1 only. So, that totally it is having 2 elements delay, right. So, this is z to the power minus 1. So, that this is S tilde n minus 2, and this has to be multiplied by alpha 2, okay, and this also will be added to this, okay, and then this goes on. I do not have the space to write down. So, I hope you can follow this. So, all this z to the power minus 1 elements will follow one below the other, okay, and then that will give us what is called as the direct form realization. So, this is nothing but a direct form realization of the filter. Now, direct form is having advantage definitely, because the direct form realization is a very simple realization, okay. It is easy to implement, but coming to the disadvantage side, that it is having I mean, it's having sensitivity, I mean, with respect to the variations in this alpha 1, alpha 2. So, variations in this alpha case make the realizations sensitive, okay, and there are alternative forms of filter realization which will be which are possible, okay. We are not going into all those details, okay, because there are some excellent references which are available, because now it is time that we have to draw the curtain on our discussions regarding the LPC analysis, because we have been spending the past few lectures at least on this. So, I think that the direct form realizations alternatives one can study oneself and then get a feel of that. Now, in this case, in the linear predictive synthesizer, there are two more aspects that one needs to consider. First is that these parameters means the pitch period and this gain, okay, how often are you required to provide this information. Now, as far as the unvoiced speech is concerned, okay, it is sufficient that if this information is given or updated per frame, okay, because it is even for a frame only that we will be having the pitch period estimation or the gain estimation. So, for every frame we are estimating that. So, and also the voiced unvoiced flag status. So, at the beginning of every frame we will be obtaining these parameters, okay. But for this unvoiced speech, once per frame should be sufficient, but regarding the voiced speech, okay, if we have a pitch period that is considered to be fixed with reference to that frame, then we have some problem in the synthesis of the speech. In fact, I mean, ultimately when we hear that segment of the speech, we will be finding that it is not a very natural speech. Why? Because that even within one frame, whatever number of pitch periods are accommodated, within that the pitch periods, okay, do vary to some extent. So that is why what we have to do is that based on the past pitch period estimations, okay, and the pitch period that is estimated from this frame, we do some kind of an interpolation, okay, so that at every pitch period, okay, we are estimating a new parameter. So this is called as pitch synchronous synthesis, okay. So a pitch synchronous synthesis is considered to be much more efficient as compared to what is called as the asynchronous synthesis. So this is a pitch synchronous synthesis, and the alternative to this is asynchronous synthesis. So what we have to do in a pitch synchronous synthesis is that for every pitch period, we have to interpolate and obtain a fresh estimate of the pitch parameter, or the pitch period estimation, okay, and then realize this, okay, then realize this linear predictive synthesizer. Now we also show that how the LPC can be used for a very good pitch period estimation, because again the success of the speech synthesis is really dependent upon how good or how accurate your pitch period estimation is. Now we just qualitatively discussed that okay, error signal could serve as a better pitch period estimation, okay, but is there any mechanism whereby using our original signal, that S of n itself, if we can filter out the formant frequencies, meaning that if we can flatten the spectrum of this S of n using any other technique, then that itself will suffice. We don't have to really go for the error signals, because the error signal again, I mean the uncorrelated part of it, okay, is a noise like thing, and there, I mean, it's not free from its inherent disadvantages. So we will be now discussing about the LPC method of pitch period estimation, okay. So LPC method of pitch period estimation from the signal itself. So in that, what we do is that we have what is called as the simple inverse filter tracking algorithm. Simple inverse filter tracking algorithm. And because this becomes a very long sentence, okay, we write it as in the short form S, I, F and T. So this is referred to as the SIFT algorithm, okay, simple inverse filter tracking. And in the SIFT algorithm, the block diagram goes like this, that here we will be having S of n as the input, okay, and then we will be having the low pass filter, and this low pass filter is going to have a cutoff in the range of lower cutoff in the upper cutoff in the range of 900 hertz. So, the filter would accept only the signals in the range of 0 to 900 hertz. Okay. And then followed by the LPF, we are going to have what is called as the decimator, and this decimator is going to decimate down the signal in the ratio 5:1. Now, what for a decimator is used? Okay, this will be very clear. The S of n is sampled at what rate? Let us say 10 kilohertz rate. Okay, and then now this is low pass filtered at 900 hertz. Okay, so at the output of the LPF you are having 900 hertz as the maximum frequency content. So what you can do is that a sampling frequency of 2 kilohertz should be good enough for you. Okay, so you need not have to keep all the 5 samples, every 1 out of 5 samples, okay, you can discard. So this is called as a 5:1 decimator. Okay, so basically it is just to downsample or to reduce the sampling frequency. So you will be getting, so you will be using the decimator. So here you will be obtaining S of n, but a decimated version of S of n after it is low pass filtered. Okay, and why this 900 hertz? What is the beauty of this 900 hertz? Because you must be wondering that we always say that the speech signal goes up to 3.3 or 3.4 kilohertz. So why are we band limiting it to 900 hertz? Well, the whole purpose of this block diagram is pitch detection. Okay, so for pitch detection we have to avoid the formants. So what we do is that by having a filtering up to 900 hertz, okay, we avoid the formants. Still the first or the second formant at the most would still be present. Okay, in fact if we have a LPF below that, then you can ask me that, okay, what if we have our LPF designed such that it is, instead of 900 hertz it comes down to 450 hertz or 500 hertz, like that. Well, the difficulty there is that the pitch frequencies variation also is often like this, because pitch is very often found to be the maximum limit, the upper limit of the pitch frequency, okay, is often found to be in the range, in the close range of the formant frequency. So that's why 900 hertz or less than 1 kilohertz is a reasonably good choice. Okay, so that only the first or the second formant frequency is still kept, but the higher formants are all discarded through this LPF process. Okay, and also the signal is still keeping the pitch period information. Okay, so this S of n, now what happens is that this S of n, what we have to do is to flatten its spectrum. Okay, so in order to flatten the spectrum we need to have a filter, and that filter is referred to as an inverse filter, where we will be having a flattened spectrum version of this S of n. Okay, and at the output of the filter we will be referring to the output as y of n. In fact, the decimated, let us call it as x of n as the decimated signal, and y of n as the output of the inverse filter. Now, what is the realization of this inverse filter? This inverse filter would be based on the LPC parameters. And how do we do that? So using this x of n, okay, we add a block which we are calling as the inverse filter analysis block. So this is an inverse filter analysis block, and we are going to have that for p equal to 4, right. So p is equal to 4 means we will be having four parameters, alpha 1, alpha 2, alpha 3 and alpha 4. So, these 4 parameters alpha 1, alpha 2, alpha 3 and alpha 4, okay, they all will be fed to this inverse filter. So, now this y of n is nothing but the flattened spectrum version of this S of n. Okay. So, now since it is flattened spectrum, what we are going to do after this in order to do the pitch period estimation, what would you expect as the block following this? Autocorrelation. So, we will now be carrying out the autocorrelation, we will be performing the autocorrelation over this y of n. So, what we do is that use this y of n. Okay. So, this is a continuation of the block diagram. Okay. So, please note that point. So, y of n would be fed to an autocorrelator, okay, or a block that performs autocorrelation, okay, and then the autocorrelation output will contain the peaks corresponding to the pitch period. So, there will be a peak detector or peak picker, whatever you can say, peak detector, and the peak detector output, again what we have to do is to use an interpolator, okay, because using the interpolator we are going to decide about the voiced and the unvoiced classification, okay, and the pitch period, the estimated pitch period is of course obtained from this thing. So, now this is really something very useful. So, so here we find a very good application of the LPC, that using the LPC parameters we are doing a kind of inverse filter and then have a better pitch period estimator as compared to the conventional approach what we had studied. Okay. And in fact, for the ease and simplicity, the LPC has become a very popular approach, a very popular and widely used methodology, okay, for speech analysis and synthesis, okay, because of its wide application. So, we have in fact studied the theory behind the LPC to a sufficient extent, okay, and we can so we will now be in a position to just integrate everything and realize what is called as the LPC vocoder. We have all the concepts available with us, okay, we know that what all are to be done, but just to assemble those blocks and realizing an LPC vocoder, okay, which we are going to take up at the beginning of the next class, okay, will really make our discussion related to the LPC complete. So, thank you for now.